All right. So welcome everyone. I see some people kind of just dropped in. Can everyone see my screen okay? Cool. So yeah, there was a question asked earlier, which is like, if we're like behind or if behind on the homework, is that okay? And the answer is like, yes, that's okay. Um, so if I mention something that you don't get, please make sure to ask questions. This stuff will basically like today we basically kind of only need to know like kind of the stuff I was talking about in lecture one. So like what is a vector, multiplying vectors by scalars and adding scalars or adding vectors to each other. I'm really excited for today's topic. I would say like today's topic is kind of the thing that one thinks about when they think about this topic. So like we're kind of learning linear algebra together. And when people think of linear algebra, the thing that they think of is what we're talking about today, which is these linear maps and matrices, which is what we'll be defining today. So I'm really excited about that. Let's begin. So let's start a little bit with this topic, which is functions on vectors. So generally speaking, when you learn about functions, you're learning about in math at least, you're learning about something that takes in some number and outputs another number, right? And so you have some input x and you have some output y, and then you have like this equation y equals f of x. Now, most of you are programmers or have done some programming, and so your definition of a function is actually kind of a better definition, which is like it's just a thing that takes in an input and produces an output. And that's kind of a very good definition. But in math, most of the time you deal with these functions that take in a real number and output a real number. But important to us is functions that take in vectors and output vectors. And so these are like functions on vectors. And we've actually already looked at some of these. So the first one is the norm. So the norm being the notion of the length of a vector or the magnitude of a vector. This function, it takes in as its input a vector and it outputs a real number. Now I've kind of been dancing around how mathematicians actually write functions, but the way that we write functions is we have like the name of the function, which in this case is, can everyone see my mouse, by the way? Or is my mouse not sharing? Okay, thank you. So we have like this norm function, which this dot here is just like a placeholder, because I don't want to just put like 4 bars right next to each other, so we put this little dot in the middle. So we have this like norm function, and it maps Rn to R. So it maps vectors to scalars. So this is how we write it in a kind of very condensed notation, because it gets annoying to write like the norm takes in vectors in Rn and maps to scalars in R. So we just write it in this condensed notation. And so this is an example of a function that takes in a vector input and outputs a number. We have another example, which is the scalar product. It takes in 2 vectors actually and outputs a scalar. And so mathematicians would write this as this kind of scalar product function. And then we have Rn, and then we have this little cross sign, and then Rn, which maps to R. And we use the cross just to indicate that there's 2 inputs. There is like kind of like a form, there's actually like a definition for what it means for like to take the multiplication of 2 sets, but we're not going to really talk about that. Like, all we really care about is that like this just means like we take in 2 different inputs, one from Rn and actually another from Rn. But these could be any 2 sets for the cross. And the third example, which I'll call P, is that we just take in a vector x, and then we multiply all its components. So if we have a vector x1, x2, x3, x4 onto xn, then we map that vector x to the product x1 times x2 on through xn, right? And so if you had a vector of all ones, then that would just map to 1. And if you were to implement multiplication in a like Lua or something, or you were to write like what it means to multiply every element in a list, that would be this function p. So these are all examples of functions that take in vectors and output numbers. In all the previous examples, right? So this is at the bottom of this thing. So I'm going to use the words function, map, and transformation all kind of to mean the same thing. And I completely understand that can be annoying, but it's kind of like it's just how mathematicians talk, and so it just like permeates my speech, right? Like it's kind of like trying to tell me not to use y'all to refer to a group. It's just very hard for me, and so what it means to map something is, right, like you can think about a function is it's giving you a function is just directions to go from an input to an output, right? And so it's what is a set of directions? Well, it's kind of like a map, right? And so that's the kind of way to think about it, is that a map is just a function. It's just a series. It's just a set of instructions from how to get from one place to another. Does that make sense? Okay. So in all the previous examples we were talking about, our functions took in vector inputs but output real numbers. They output scalars. We can do better, or not better, but we can do different, which is that we can have functions that take in vector inputs and output vector outputs. And we call these things vector valued functions. So in general, just if you have some function f that takes in some input and outputs a vector, then that's called a vector valued function, because the values that it outputs are vectors. And usually the inputs will also be vectors. But really, vector valued function just means the output is a vector. So that's, if I say vector valued function, I just mean a function whose output is a vector. A good example of this, and kind of the trivial example, is if you have the function that just maps a vector to itself. So it takes in x and outputs x. Then this is a vector valued function because it outputs a vector. But it's a very special one, and we like to give special things special names, and so we call it the identity map. And so it maps everything to itself. It's actually a very important map, so it'll come up a lot next week, and actually throughout the rest of the course, because it basically like represents doing nothing. Sorry, my scroll wheel is broken, so I sometimes scroll too far. So now we've talked about things you can do with vectors. So the first, one of the first things we talked about was like you can add vectors, and the second thing we talked about is like you can multiply vectors by some scalar, some real number. And so that's really important. It's really important that we can do that. It's really important that we can add and scale vectors. And sometimes we want to do both at once. So we want to add scalar multiples of vectors. And so, again, mathematicians like to give special things special names. And so we're going to call such a sum a linear combination. And so if we have some list of vectors, and again, I'm using this superscript because subscript means element. So it's like x1 through xk. These are all different vectors. That's not a power. So a linear combination of those vectors is just a sum of those vectors times some scalars. So this is very useful, and so if I ever say linear combination, I just really mean a sum of vectors times some scalars. You can think of this as like a weighted sum, right? If I just added up all the vectors, that would give me, that's technically a linear combination. But I also can like add some weights to them, which are these alphas. And so that's a linear combination. Now we talked about vector valued functions, but one of like the most interesting properties that a vector valued function can have is if it distributes over these linear combinations. And I'll talk about what I mean by that, but this kind of distributing over linear combinations is like a very important property. And as I keep saying, we like to give these things names. So if a vector valued function distributes over linear combinations, then we call that function linear. So in particular, if we have this map T, and it's going to map Rn, so it's going to map vectors with n elements to vectors with m elements, and we're going to say that that function is a linear transformation if whenever we have some linear combination of vectors in Rn, we have this distributive property. So the T basically distributes over this sum. So in particular, like if you have T of alpha times x, then it's just alpha times T of x. And if you have T of x plus y, it's just T of x plus T of y. And you can show if you want that the identity map is linear. And the way you show that is basically just that, T of x1 is just x1, and T of this whole sum is just the whole sum. And so you can show these two sides are equal. But the norm is not linear. So this is a very important definition, and so I want to make sure, does everyone understand what I mean by this? Are there any questions about it? I see one person typing. So so the question was if a linear transformation is a function that takes in and outputs linear combinations. Not quite. So a linear combination of vectors is a vector, right? So if I scale a bunch of vectors and then I add them all together, I'm going to get back a single vector, right? So you could replace this whole input with just some vector that we'll call y. You could do that. So then what this would be saying is that T of y equals this sum. So it's still taking in a single vector. It's just that that vector we've just written that vector as a combination of other vectors, and then it distributes. Does that make sense? The kind of two most important properties are actually these bottom two. So if you ever have T of some vector added with another vector, it's just you add them at the other end. The kind of way, no, I'm not going to get into that. We'll do some examples, but we'll do one example actually. Yeah. Trying to think of a better way to explain it. We'll see if going on helps. So a bit of motivation for why we care about these things. So it's really difficult to describe exactly how important linear transformations are. So like I was going to say that linear transformations are the most important object in mathematics, but this isn't really true because you have to like first have like logic, and then you have to have sets, and then you have to have functions. Because if you don't have those three things, you can't do math. But after those three things, after those three completely essential things that you literally need to do any math at all, the next most important object in mathematics, I would say, is the linear transformation. So, every application of mathematics to any field is going to be based, at least in part, on these types of functions. Like the things that the computers are doing to like keep the power grid running, that's all linear transformations. Things that predictions that people make about the economy, stock trading, all that stuff is linear transformations. Like physics is almost entirely based on linear transformations. There's entire ways of thinking about physics where you just turn everything, you turn energy, you turn mass, you turn momentum, everything into linear transformations. Machine learning, ecology, medicine, data science, image processing, audio processing, computer graphics, like the way that you represent where things are in Roblox, like everything, like every field of math, every like field of applied mathematics, every field where math is used, linear transformations are probably at the heart of it. And like there are entire fields of mathematical study devoted to taking things that are not easily understood as linear transformations and making them be linear transformations. And yeah, if I could change anything about the education system in mathematics, I would basically replace calculus with linear algebra, which is the study of linear transformations. At least in America, like calculus is like the final destination in high school math. And if you're like particularly precocious and you're ahead of other people, I would change that destination to linear algebra, and if I could only do one thing. They're super important. But back towards linear transformation. The question was asked, is Gram-Schmidt a linear transformation? Oh, it's not, but only because it takes in a list of it takes in a set of or a list of vectors. And outputs a list of vectors. So it's not exactly a vector valued function. You can make sense of it as a vector valued function, and then it has weird properties. But the answer is kind of like no, but kind of yes. Sorry, that's a little bit vague, but we'll actually talk about it later. Oh, not this week, but another week. Let's work on understanding linear transformations a little bit more. We've got this linear transformation T, and it's mapping vectors in Rn to vectors in Rm. So it's mapping vectors that have n entries to vectors that have m entries. And it's a linear transformation. Now we're going to work with this same linear transformation T for a while. So if I say T throughout the rest of the lecture, what I mean is this T, unless I say otherwise. Now we've got these list of vectors that I've talked about a few times now, where it's E1 is just 1 with a bunch of zeros after it. E2 is 0, 1 with a bunch of zeros after it. And En is just a bunch of, we go up to En, which is a bunch of zeros followed by a 1. And these are all vectors in Rn. So there are n. Oh, I forgot to put a 0 here. That's my bad. There should be a 0 right here. These are all vectors with n entries. Now we have x as this vector here with x1 through xn. And we can write, if you kind of unpack this, if we take the scalar x1 and multiply it by e1, we'll get x1, 0, 0, 0. And then if we take x2 times e2, we'll get 0, x2, 0, 0, 0, 0. Right? And so if you do all the algebra and work everything out, you'll get that you can write x as a linear combination of these EI vectors. This is a kind of very useful thing. We call these EI through ENs the quote-unquote standard basis, which is it's actually, we defined what an orthonormal basis was. So this is actually an orthonormal basis for Rn, but don't worry too much if you don't know what that means. So basically, you can write X as a linear combination of elements in the standard basis. And now, if you believe me that this T is linear, which I've defined it to be linear, but so if T is linear, then we have this like T of X, right? And we can write X as this linear combination of EIs, right? So we have like T of X is equal to this linear combination. And then by the property that we showed, of what it means to be linear, we can distribute this T, right? So this T goes to E1, goes to E2, goes to E3, goes to En. And so we end up with a linear combination of these T of EIs, right? So if I know these values, oh, this should be a superscript, sorry. If I know these values, then I can actually find T of X for any X I want, right? Because if I know what vectors these are, I just look at X, I ask what are its components, and then I take the first component times this value, plus the second component times this value, on and on until we have the nth component times this value, right? And so you end up with this linear combination. So as long as we know these n vectors, then we can easily find any value of T of X that we want. And so we're going to call Ti, we're going to say that Ti is this vector here, because we'll be talking about the Ti's a lot. Does this make sense, what I just did here? And I hope this also makes it a little bit more clear what I meant when I said, like, it takes it, sorry, hiccup there. It takes in a single vector, but then, like, you can expand this vector as a sum of other vectors, and then it distributes. I'm gonna take a drink real quick. So the question was asked, so they can take in anything isomorphic to a list of vectors. Isomorphic here meaning like the same form. The answer is no. They take in just one vector. So linear transformation maps a single vector to a single vector. But you can write a single vector as a sum of other vectors. And when you do that, you can then distribute. Yeah. So you've got, we went through and like defined what these TIs are. And so we have a list now. We have a list of vectors. Ooh, that's kind of interesting, right? And all these vectors are in Rm. So each of these vectors in here has m entries. And so we have a list that's n long of vectors, and every vector is m long. So, whenever we have a list of values that are scalars, we write them as a 1D array. We write them as this like one-dimensional list. So if we wanted to write out the values of this list of vectors, it would make sense to put these into a 2D array, where we have this array A, and it's two-dimensional, so it has length and it has width. And for this 2D array, its columns are going to be the TIs. I made a typo there. That should be a superscript as well. Now we're going to talk about these 2D arrays a lot. and we're going to talk about some properties that they have. And so we're going to call these 2D arrays matrices. So fundamentally, a matrix is just a 2D array where every element in that 2D array is a scalar. So we're gonna say that M super X cross N is just the set of all matrices with M rows. So that's like rows are like going left to right, and N columns. So columns are going up and down. Now we're always going to write matrices as capital letters. If you work it out, then this matrix A has M rows and N columns, right? Because the columns are T1 through Tn, so there's N of those. And then each of these Ti's has M values. So like each column is M tall, so it has M rows and N columns. Decided to disconnect. So sorry about that. My headset just decided it didn't want to be connected anymore. Whoops. Anyway, so we're going to write A sub I to be the ith row of this matrix A, and A sub I, ij will just be like the entry stored at the ith row and jth column of A. This would be an example of how we write a matrix. Given a vector, right? So a vector is like this 1D array. We could pick two possible ways of writing them. There are two matrices that have the same entries, right? So we have this vector x1, x2, xn. Now we could either stack these as a column, or we could write them as a row. And normally when we write vectors, or we write them as these lists, and their lists look like rows, right? So you may be tempted to think that whenever we're writing a vector as a matrix, which is basically what we're trying to define here, that we want to go with a row. And this is not true. For reasons that are often mysterious, we decide that whenever we write a vector as a matrix, so whenever we want to write a vector, we want to have a matrix that has the same entries as that vector, then we choose to write it as this column. And so we call this a column vector. And so everything we've ever talked about with vectors also works with column vectors. So you can take scalar multiples of column vectors, you can add column vectors, you can take the scalar product of column vectors. It's just another way of writing down the same list. And if you want to know why we picked it to be a column, kind of the answer is that if you don't pick it to be a column, then instead of writing f of x, you'd write parentheses x f, which there are some mathematicians who do that, and they are crazy. Basically, as long as you want to do everything the kind of standard way, then we decide to choose x to be a column vector instead of choosing x to be a row vector. And now I am going to I will often not differentiate between column vectors, which are these matrices that are these columns, and vectors written as lists, like this. And so if I say a vector, you can either think of it as this column, or you can think of it as this list, and those are pretty much exactly the same. As Borb just said in the chat, the only difference between a column vector and the kind of list vector is that they're the same thing written differently. But it's very convenient to write them as column vectors, as we'll see in a couple slides. But yeah. Are there any questions about like column vectors or like actually matrices? That is always the question. The question was asked, why column vectors? Um, so again, the kind of, okay, so we're going to talk about, so basically like the kind of short answer they'll give, and this is not a very satisfactory answer, but if you want everything to kind of work out nicely with matrices, we would have to, instead of writing t of x, so putting this of on the right hand side, you would have to move this parenthesis thing to the left of t, and so it would be open parentheses x close parentheses t equals. It's just terrible. But so basically, if you want all of our conventions to work out nicely, then you have to pick column vectors instead of row vectors. That's kind of all I'll get into it, because it doesn't really matter as long as we all agree on the same thing. And the thing that the community has agreed to do is treat vectors as column vectors. Yeah. So now we get to the good stuff. So we've got this matrix A, right? And this matrix A we constructed so that its columns are these TIs. We know that we can expand this T of X as this sum here. And so we kind of want to define what it means for like A of X to mean this, right? Because we want like A contains all the same, like contains all like the vectors Ti, and these are all the vectors Ti. So we want this to be true. We want this here. But for reasons that will become clear eventually, instead of writing like A of X, we're actually just going to define this to mean like, what does it mean to multiply a matrix by a vector? And we will use this definition. We will take this to be the definition of multiplying a matrix times a vector. So if you wanted to write it all out in glorious matrix notation, your matrix A would look like the thing on the left. Your vector X is this column vector, and the resulting sum looks like this. Now it's a little bit deceiving, but this is actually a different height than this. These dots are kind of different, because this is m tall and this is n tall, and m and n can be different. It just kind of works out that way if you do it typographically in LaTeX. So this is a height n vector. This is a height m vector. And note, this is a vector. This is genuinely a vector. It's a column vector, because each of these are sums of products of scalars. So everything in this column, this is a column vector. And so this is our definition for matrix multiplication, at least for a matrix to a vector. It's a useful definition. Are there any questions about it? All right. So, yes. Now, we've basically said like we can multiply a matrix and a vector, right? So far we've been working with this same matrix A, right? And so A was defined by first taking a linear transformation and then figuring out what the T of Ei's were, and then those are the columns of our matrix. And so, but we've now kind of defined this like very general form of matrix multiplication, or you could at least generalize it, where if you ever have any matrix A, you multiply it by any vector X, you just get this sum where you replace the TIs with just the columns of A. And so, what are the conditions necessary to multiply a matrix and a vector? Well, the answer is if A has m rows and n columns, then the vector X, written as a column vector, has to have n rows. So see, like the number of columns that A has to be equal to the number of rows that X has. So that, and it will produce, oh, this is the typo, that should be Y. It'll produce a vector with M entries. So we multiply it, A times X, this resulting vector here is going to have M entries in it. And takes in a vector that's size X. But, think about how we talked about matrices in the first place. The way that we constructed our very first matrix was we took a list of vectors and then said, we can just store that in a 2D array. But we can do the reverse. If I have a matrix B, we can think of it as a 2D array, or we can think of it as a list of its columns, right? Okay, so now we have a list of vectors. Well, each of those vectors will be a column vector with n rows. So it'll be a length n column vector. We know how to multiply a matrix A with a length n, that has n columns with a length n column vector. So right, we know how to do AX when X is in this space here. So we can just multiply every column of B by A to produce a vector, another vector, right? So by multiplying by A, we get this list of vectors. Now I'm going to pull up impromptu MS Paint to demonstrate this. So let me change my window real quick. Sorry, this is completely impromptu, right? So we have this list. Let's call the columns of B. We'll say that the B. Can you all see this? Okay. So we have like this. It has K columns. So there's this matrix here. This is n tall and k wide. Okay, and so we can basically, right? We can just do A times B one. We can do A times B2, comma A times B3, on and on until we get to BK. And this is now another list of vectors. Each one of these vectors is going to be in Rm. And so, again, we can do the same thing. We can just make the matrix whose columns are these new vectors. We can just say C, we can just define this new matrix C, and its columns are going to be A, B, B1 through A, BK. And this is a matrix. And so we've taken, and so this is a good way of multiplying matrices. We've taken two matrices, we've multiplied them together by multiplying A times every one of its columns to get a new matrix C. And this is actually how we're going to define matrix multiplication. So, given two matrices, A and B, now the number of columns that A has to be equal to the number of rows that B has. But as long as that's true, we can define their product as this matrix C. And it's going to be the matrix whose ith column is A times the ith column of B, just like we just did. So an example of this is you just take, like here, this is the 2x2 matrix. This could be our example A. And so what do? Well, we take the first column of our matrix, and we multiply it by the first entry of this matrix, column vector, and then we take the second column of this matrix and multiply it by the second entry, and we add those up, and that gives us 7, 3 as a new column vector. And then we do the same thing here. This is a little bit more illustrative. We take the first column of this vector, we take the first column of this matrix times the first entry of this column vector, and that gives us this. Then we take the second column of this matrix times the second entry of this vector, and we get this, and then we add them up, and that gives us 32, 13. And so, if we want to multiply these two matrices, the first column of the resulting matrix will be this column here, which is just this product, and the second column of the resulting matrix will be this here, which is just this product. And so that's how we multiply matrices. Now, if you look it up online, you'll probably see some other kind of nastier definitions of multiplying matrices, and they're not wrong. That's actually like how you would compute it on a computer. But this is kind of the way that I do it in my head. This is the way I recommend people think about multiplying matrices, and it's also a very useful way of thinking about multiplying matrices. As long as you can multiply a matrix and a vector, so as long as you can do A times X where X is a vector, then you can do matrix multiplication for any matrices. So, the advice I would give is if you're going to spend time learning this, which I hope you are, spend time understanding matrix vector multiplication. Spend time understanding how you multiply a matrix with a vector. And then only once you understand that, try and understand how you multiply two matrices. And kind of the whole way that we derived these matrices, the way that we started with linear transformations, and then talked about like applying linear transformations to each of the standard basis vectors to get the columns of a matrix. This is very useful, and this is basically why we care about matrices. What I walked through for you today is basically, if you give me a linear transformation, if you give me a function that I know is linear, I can give you a matrix that will basically do the job of that function, right? So if you look at our definition for applying this matrix to a vector, note the way we've defined it, multiplying x by a is the same thing, gives us the same vector as applying t to x. So really, applying t to x is identical to matrix multiplication, and that's why we defined it that way. That's how we defined it that way. So if you kind of can go through that derivation, if you can understand like the steps that we took, then this thing, matrix multiplication, which is often very complicated, and I know I really struggled with it when I first learned linear algebra, it really becomes this very simple thing, where it's just like as long as you can multiply by vectors, you're okay. So that's what I recommend doing, like kind of figuring out what exactly matrix multiplication does when you're multiplying by a vector, so matrix vector multiplication, then trying to figure out matrix multiply. And now kind of the other thing, yes, so the thing you should get used to is matrix times vector. The way we've defined it right now, you cannot do vector times matrix except in very specific circumstances, because to do that, your matrix would have to be a 1 by something matrix, right? Because a column vector is n by 1, and so if you're multiplying vector by matrix, you'd have to have a 1 by m matrix on the right. But so for now, just focus on matrix times vector. And then once you feel comfortable with that, you can move on to matrix times matrix. And from now on, if you ever hear the term linear transformation, you should think matrices, because you can always do what I've just done, right? You can always take some linear transformation T and then define a matrix whose columns are these values here, and then that matrix will do the same job as your original linear transformation T. And so in a sense, T and A are actually equal, but not really. It's just like A is just like a way of writing down T. It's kind of a way of thinking about it. But yeah, we're gonna end a little bit early unless you guys have questions. More than happy to answer questions. So there's already a question, which is matrix vector multiplying each column of the vector by a corresponding component? Oh, you mean each column of the matrix? So yeah, so matrix times vector is you multiply every column of your matrix by a component of your vector, and then you add all of them up, if that makes sense. Yeah, so let's go back to the definition then. So, right, here's like the definition, right? So these TIs are the columns of A. Does that make sense? Okay. And these XIs are the components of X. And so we're taking the scalar product, or sorry, the scalar multiplication x1 times t1 plus x2 times t2 plus x3 times t2, 3, on and on until we get to xn times tn, right? So it's fundamentally we're like multiplying and then we're adding up. It's very similar to when we did the scalar product, right? When you do the scalar product between two vectors, you multiply all the components and then add them up. But in this case, the components, quote unquote, of A are just its columns. Does that make sense? Sure. I'm going to end the recording.